The atmosphere of a planet or moon is the gas bound to it by gravity. As we look around the solar system, we see an incredible variety of atmospheres, from the thin, cold air on Mars to the huge, dynamic hydrogen atmosphere of Jupiter. We also find that atmospheres have complex interactions with the surfaces of worlds such as the Earth or Titan. We'll start by giving an overview of the different kinds of atmospheres around the solar system. Then we'll look at the structure of an atmosphere, focusing on how the pressure and temperature change with altitude. Looking more closely at atmospheres, we'll see some of the major factors that drive climate and weather, including seasons, winds, clouds, and precipitation. In the second part of the chapter, we'll discuss the ways an atmosphere can form and how a world can lose its atmosphere over time. Finally, we'll look at long-term climate change in the atmospheres of the terrestrial planets. This will let us introduce the important topic of feedback systems, as well as some of the ways humans are currently impacting our global climate. An atmosphere is the gas surrounding a planet, moon, or star. For us here on Earth, the atmosphere is the air that we breathe. An atmosphere is a dynamic system. In other words, atmospheres are constantly changing. Processes like wind, evaporation, and sublimation operate on timescales of minutes, hours, or longer, while seasons change throughout the year, and other forms of climate change and evolution can operate on timescales of thousands or even millions of years. So remember that an atmosphere is never completely static. It's always changing at one level or another. Now let's look around the solar system at some of the different sorts of atmospheres that exist. Among the terrestrial planets, the thickest atmosphere belongs to Venus. This thick, hot carbon dioxide atmosphere gives Venus the hottest surface in the solar system, hotter than an oven on self-cleaning mode. The clouds are made of sulfuric acid, though the sulfuric acid rain evaporates before it reaches the surface. Mars has a much thinner, cooler atmosphere, also made mainly of carbon dioxide. While the Venus atmosphere is almost 100 times thicker than the Earth's, Mars' atmosphere is over 100 times thinner than the Earth's. Nonetheless, there is enough air on Mars to carry large dust storms that can cover the entire planet. Earth's atmosphere is intermediate between Mars and Venus in both temperature and pressure. However, the composition of Earth's atmosphere is completely different. It's made of mostly nitrogen and oxygen, with less than 1% carbon dioxide. The Earth is also the only terrestrial planet with substantial water clouds, not to mention a thin layer of water over much of its surface. We call this the oceans. Finally, the Moon and Mercury have incredibly thin atmospheres, so thin that we often say they don't have an atmosphere at all. However, there is a tiny amount of gas held by both of these worlds. Moving on to the outer solar system, the Jovian planets all have very similar atmospheres. These are thick layers of hydrogen and helium, much thicker than the atmospheres of any of the terrestrial planets. When we look at the Jovian planets, all we see are clouds, often multiple layers of clouds at different altitudes in the atmospheres. For Jupiter and Saturn, these clouds are mostly ammonia and ammonium hydrosulfide, though there's probably a layer of water clouds deeper down in the atmosphere where it's warmer. For Uranus and Neptune, the clouds are mostly methane. It's also methane gas in the atmosphere that gives them their blue color, since this gas absorbs red light very efficiently. Remember that none of the Jovian planets have solid surfaces. Instead, as you go deeper into these atmospheres, the pressure and temperature keeps going up until finally you reach the point where hydrogen is squeezed into a liquid far below what we can see from outside. In this slice through Jupiter, the gaseous hydrogen is the region at the top of the planet. It's only a small part of the whole planet. Nonetheless, this is a depth comparable to the radius of the Earth. Just like the Earth's moon, most moons of the Jovian planets have little to no atmosphere. A few of the ones that are geologically active have slightly higher gas pressures. Saturn's moon Enceladus and Neptune's Triton have noticeably more gas in their atmospheres than most other moons, though it's still far less than we see for even a small planet like Mars. These atmospheres are produced by the active geysers on their surfaces. However, one spectacular exception to the trend of moons with very little atmosphere is Titan. This large moon of Saturn has a thicker atmosphere than Earth. The air pressure at the surface is 1.5 times as great as we have here. Titan's atmosphere is in some ways the most similar to Earth's. It's dominated by nitrogen gas, though the next most common gas is methane. There are clouds and even rainfall feeding lakes and rivers on the surface, all made of liquid ethane and methane. All of this gives Titan one of the most complex atmospheres in the solar system, and we're only just starting to study it in detail. Let's start our study of atmospheric structure by looking at pressure. Pressure is defined as force spread out over an area. In the case of gas in an atmosphere, the local air pressure at any given spot is the weight of a column of air over that location. Remember that weight is a force given by the mass multiplied by the acceleration due to gravity. So the weight of an atmosphere will depend on how much mass there is in a column of air and on the strength of gravity of the world. For example, a column of air on Titan has about 10 times as much mass as a column of air on the Earth. However, Titan's gravity is much less than the Earth's, so the air pressure is only 1.5 times as much on Titan's surface as it is on the Earth's.
You can get the main idea about pressure changes in either the atmosphere or the ocean from this your turn. If the weight of the Earth's whole atmosphere pushing down on sea level gives a pressure that we call 1 atmosphere, then what is the pressure at depth A, at depth B? Notice that we chose A to be 10.3 meters down, under a depth of water weighing just as much as the atmosphere weighs, and B is another 10.3 meters down. For you panicky folks, this is as easy as it looks. No trick question here, but do explain your answers. Now describe how pressure changes as you go up in an airplane.
The air pressure on the Earth's surface at sea level is described as 1 atmosphere pressure. This is also called 1 bar of pressure. As you go higher up in the atmosphere, the air pressure drops. On the Earth, every time you go up another 5,500 meters, or 5.5 kilometers, the air pressure drops in half. This is almost entirely due to the fact that there's less air above you, so the weight of the column of air is less. Note that changes in the amount of gravitational pull play very little role here. If you go 100 kilometers up on the Earth, the air pressure has dropped to much less than 0.001 atmospheres, but the gravitational pull is almost as large as it is on the ground. Lastly, while the air keeps getting thinner as you move upward, there isn't a clearly defined end to it. Instead, the air keeps getting thinner and thinner until it simply merges with the gas between the planets, the interplanetary medium. Notice this picture of the space shuttle. We're looking towards the tail section of the shuttle while in orbit hundreds of kilometers above the Earth's surface. The reason it's glowing is that even this far up, the shuttle is still moving through a tiny amount of air at a speed of 8 kilometers per second. When it collides with gas molecules at this high speed, the energy of the collision causes the gas to light up, producing the glow you see here.